Okay guys, this is discussion 1-2. It's a review of gas behavior and solutions. So we're going to go through this. I think the gas behavior you'll probably be pretty comfortable with. You may have some questions on solutions and molarity, but feel free to bring those to class and we can go through whatever you like. Okay, basic gas law relationships. Pressure and volume. As the volume increases, the pressure decreases. You can also think about it in the opposite way. If you take a balloon and squeeze the balloon, the pressure will increase, and if you squeeze it enough, the pressure will become so great that the balloon will break. So this is an inverse relationship, and we can write it this way mathematically. Pressure and temperature have a direct relationship, so as the temperature increases, the pressure increases. Think about taking a can and throwing it into a fire, an aerosol can. It would explode, right? Because you would increase the temperature so much that the pressure would increase to the point where the container could no longer hold it. So this is the relationship between pressure and temperature. And temperature and volume is also direct. As temperature increases, volume increases. Think about heating a balloon. If you increase the temperature of the balloon, you would expect the volume to increase as well. And that's the relationship between temperature and volume. So if we combine the three relationships, we can put them together like this. This is called the combined gas law, and the really convenient thing about this is that if I want to study all three of these factors together, I can, but let's say volume stays constant. Well, then I can cancel it out, and I have the relationship between pressure and temperature. Works for any of those variables remaining constant. The ideal gas law, PV equals nRT, hopefully you remember that from Chem 1. We can use this to derive all the other relationships as well. By setting PV and T equal to NR, which stays constant, I get my first half of the combined gas law equation, and we'll go over this in class. So look at these two practice questions. Think about them. These are more conceptual questions than they are mathematical, although you could do them mathematically. So take a minute, pause, think about the answers, and then we'll go over them. Okay. If you double the temperature, the Kelvin temperature, you would expect that what would happen to the pressure? It should double, right? Because pressure and temperature have a direct relationship. If I triple the temperature and the volume of a gas, what is the effect on pressure? Well, there would actually be no effect because the increase in volume and the increase in temperature would cancel each other out, since temperature has a direct relationship with pressure and volume is inverse. Okay, now, hopefully you remember molar volume from Chem 1. We talked a lot about STP, which is standard temperature and pressure. So STP is standard temperature and pressure, and the standard temperature is 273 Kelvin. The standard pressure is 100 kilopascals. Now, this is actually a little bit different than what you learned in Chem 1. In Chem 1, you learned that it was 101.3, and that's actually technically slightly more correct. But people have started to use 100 kilopascals because it's more of a round number and it's close enough to 1 atmosphere. But this is going to change something else important that you learned. So at STP, what is true of gases is that 1 mole of gas occupies 22.7 liters. Now in Chem 1, you learned 22.4, but because of the slight change in the value for pressure, it's going to be just a little bit different, okay? This value is actually given in the data booklet, so it's not something you need to be too worried about. And here's the mathematical proof of why that's true. Okay, so let's look at an example of how we can use these molar volume relationships to solve problems. Now these are fake gases. We're going to assume they're all gases. It says 2 liters or decimeters cubed of gas A is reacted with excess gas B at STP. One important note on units, hopefully you've noticed that we're using decimeter cubed. That's the same as a liter, but that's closer to the SI unit, which is meters cubed. Okay, so we know that this is at STP, so we know that there are 22.7 decimeters cubed per mole. So we could do it this way. We could convert decimeters cubed of A to moles of A, use the mole ratio to get moles of C, and then convert back to decimeters cubed of C. Okay, but one thing you hopefully notice is that that 22.7 cancels out, right? Because we're saying that the mole ratio is also a volume ratio, because they're directly related, we can just shorten it. Okay, we can go straight from liters of one to liters of another. Okay, so again, that's because moles and volume are directly related. The mole ratio is also a volume ratio. Okay, now we don't often have STP conditions, but that trick of using the mole ratio as a volume ratio will work in any case as long as the pressure and temperature remain constant throughout the reaction. Okay, so it doesn't actually have to be STP for you to use the mole ratio as a volume ratio. Okay, so try this next problem. A 400 centimeter cubed sample of hydrogen gas is reacted with excess oxygen gas to produce water vapor. Now, centimeters cubed, that's the same as a milliliter. So a 400 centimeter cubed sample would be the same as a 0.4 decimeter cubed sample. And we want to find out what the volume of water vapor formed is. Now you want to first write a balanced equation for the reaction of hydrogen and oxygen to produce water vapor. Okay, so try this problem, pause this, and then resume when you're ready to see the answer. Okay, hopefully you came up with this for your balanced equation. Don't forget that oxygen, like hydrogen, is a diatomic molecule, so it's O2, not O. And because this is at a constant temperature and pressure, we can assume that, we can use the mole ratio as a volume ratio, and we're talking about all gases here. Okay, and so you would get 400 centimeters cubed of water vapor as well. Okay, now we're going to switch and talk about molarity and solutions. This is something we don't spend quite as much time on in Chem 1, so this may be an area where you have a few more questions, but just jot down any questions you have as you're going through this or highlight them, and then we'll talk about it in class. So molarity is a measure of concentration. In Chem 1, we represented this with just a capital M for the unit. The proper unit is really moles times decimeters to the -3. So that means moles divided by decimeters cubed. So that means moles per liter. Okay? So if I were to tell you that I had a 5 mole per decimeter cubed solution of HCl, that would be the same in a lot of American textbooks. You'll see it written as 5 capital M or 5 molar HCl. And that's the same thing as saying there's 5 moles of HCl per 1 decimeter cubed of solution. Now, a common problem you see with molarity is a dilution problem. And for dilutions, we use this formula. The molarity of the concentrated solution times the volume of the concentrated solution equals the molarity of the dilute solution times the volume of the dilute solution. So why is this true? Why can we take something a little more complex and put it into such a simple expression? So when I dilute something, that means I'm adding water. I'm not actually changing the number of moles, right? If I have concentrated acid and I add some water to it, I haven't added or taken away any acid, right? Since molarity times volume equals the number of moles, basically what I'm saying is the original moles equal the final moles. Okay, so try this problem. It's asking how you'd prepare a 400 milliliters of a sodium chloride solution with a concentration of 0.2 moles per decimeter to the -3. Okay? So take a minute and think about this problem, see if you can solve it, and then we'll go over it. Okay, now we know that molarity is moles per decimeter cubed. Okay? So we were given milliliters, and that's the same thing as liters, the same thing as decimeter cubed. So if I start with 0.4 liters or decimeters cubed, I can actually use molarity as a conversion factor to go from decimeters cubed to moles. And then I can convert from moles to grams, just like I did all through Chem 1 and in the last topic. So I get 4.68 grams of sodium chloride. However, it's important to note here that that's actually not what the question asked. It asked, how would you prepare 400 milliliters? So the first step is figuring out how many grams you would need, but then I need to actually describe how I would make the solution. So I'd measure out 4.68 grams of sodium chloride. I'd add it to a small amount of water in a 400 centimeter cubed volumetric flask and dissolve, and then I would dilute to the mark. Now, a volumetric flask is a very precise, calibrated piece of glassware that we don't use in Chem 1 very much, but it's a lot more precise than using a graduated cylinder. And they come in specific sizes, and they just have one mark that's that exact size. Important thing here, though, is that the math alone doesn't answer the question. You could have also answered this by talking about using a graduated cylinder, but you would need to actually talk about the lab procedures. Okay, try this next problem. This is sort of a problem that requires you to think conceptually about molarity. So pause this and then resume when you're ready to see the answer. So I think that one thing that is a little challenging for people when they first start to look at molarity problems is that complex unit for molarity, moles times decimeter to the -3. It'll help if in your head you kind of think, okay, that means moles per liter, and I have 2.5 liters, okay? So there's a couple different ways you could do this problem. Let's look at one of them. So the first thing I need to know is if I'm just talking about chloride ions, well, how many moles do I have? So I can take my liters of iron 3 chloride and convert to moles of iron 3 chloride using the molarity. Now I know that for every molecule of iron 3 chloride, I'm going to produce 3 chloride ions when it dissolves. So the same thing is true when I talk about moles instead of molecules. For every 1 mole of iron 3 chloride, I'll produce 3 moles of chloride ions when it dissolves. So then I get 3.75 moles of chloride ions. Since I want the molarity, I then need to divide by the volume again to get the molarity of 1.5. Another way to think about this that's a lot shorter is say, okay, if I know the concentration of iron chloride, and I know that for every 1 iron chloride, I produce 3 chloride ions, well, the concentration of chloride ions must be 3 times greater. So I can just say the original concentration times 3. It's important if you're using dimensional analysis with molarity. It can be really hard to know where to start, right? Because there's 2 numbers in that problem. So one important thing is try not to start with molarity. Because it's a compound unit that involves both moles and decimeters cubed, it's more useful as a conversion factor. Okay, let's look at a dilution. We talked about that dilution formula before. So go ahead and try this problem. Pause and then come back when you're ready and look at the answer. Okay, so we're diluting a solution, so we're going to use M1V1 equals M2V2. Okay, now it's really important here that you keep things on the right side of the equation, right? We know that the concentrated solution has a molarity of 18, and we want to know its volume, so that's our variable. On the right side of the equation, we know that we want to make a 0.5 mole per decimeter cubed solution, and we want to make 2.5 decimeters cubed of this solution. Okay, so we can easily solve for the volume of the original solution, and we get 0.0208 decimeters cubed, but it actually asked us for centimeters cubed, so then we need to convert from decimeter cubed to centimeter cubed, and that's basically liters to milliliters, so you multiply by 1,000. Okay, last problem is a titration problem. Now, this says what volume of 0.1 mole per decimeter cubed H2SO4 is needed to neutralize 50 centimeters cubed of 0.3 mole per decimeter cubed NaOH. For titrations, the number of moles of H plus are equal to the number of moles of hydroxide at the equivalence point. So you might remember from Chem 1 when we did titrations, the color changes at the equivalence point. So we can derive this formula. The number of moles of H plus times the molarity of the acid and the volume of the acid equal the number of moles of hydroxide times the molarity of base times the volume of base. So H2SO4 has 2 moles of H plus and NaOH has 1 mole of hydroxide. So this is what we would get. 2 times 0.1 times the volume of the acid equals 1 times 0.3 times 0.05. So the volume of the acid we would get is 0.075 decimeters cubed or 75 centimeters cubed of H2SO4. Okay, that's it. Bring your questions to class tomorrow and we will go over them.